All right, let's get into it. Today we're doing a deep dive on something that's kind of a silent killer in server rooms.
Oh, yeah.
Unstable power. Specifically, we're looking at the NTI E-ACLM-V-V2, which is an AC dual voltage monitor.
Right. A very specialized piece of kit.
And our mission here is really to understand how this hardware takes these tiny, subtle fluctuations in power
The ones that can be so destructive.
and turns them into actual hard data, something you can act on. It's about preventing failures, not just reacting to them.
Exactly.
So what's this device actually watching, and why is that dual input so important?
Well, you can think of it as system insurance, really. It doesn't just check if the voltage is there. It's actively monitoring the AC line input from two completely separate lines.
So that's the dual part. That's the key.
That is the key. You get an immediate comparison, which means you have true redundancy. And it reports back just two main things to the Envirom-UX system.
Which is like the central brain for all this environmental data.
Precisely. It sends back the RMS AC voltage and the AC frequency, the hertz, and it's built to work globally, anywhere from 50 to 250 volts.
Okay, so that dual monitoring alone really raises the bar for resilience. But the real magic isn't just knowing the power is on, is it?
Not at all. The steady state is the easy part.
It's about catching those really quick events, the transients that just kill equipment. I see here it tracks swells, sags, and spikes. So in plain English, what kind of damage are we talking about?
I mean, you can almost think of them as the three horsemen of power quality failure.
Right.
A sag. That's basically a quick brownout. The voltage dips suddenly, and that's what causes those random reboots or system instability.
The kind of stuff that's impossible to trace after the fact.
Exactly. Then a swell is the opposite, a momentary surge that really stresses components, but the really nasty one is the spike.
And that's the one that just fries things.
Instantly. They're incredibly brief, very sharp overvoltage events, just notorious for frying delicate electronics.
Now, you mentioned precision. Our sources say this thing uses 12-bit ADC resolution and gets 1% accuracy. For the non-engineer, what does that actually buy you compared to, say, a standard surge protector?
That precision is everything. That 12-bit ADC means it's taking thousands of super detailed measurements every single second.
Wow.
And that 1% accuracy means it can catch an event that lasts for just milliseconds, something a consumer device would completely miss or just write off as noise.
So this is basically high-fidelity electrical surveillance.
Single data centers, yes.
And this is where it gets really interesting for anyone listening. The spike detection is customizable. You can set it to detect a spike anywhere from 50 volts all the way up to a kilovolt. Why would you need a threshold as low as 50 volts?
That's a great point. That low 50-volt threshold is for your most sensitive equipment. Think specialized lab gear, delicate networking components.
Yeah.
Things that react badly to even minor changes.
Okay, I see.
Whereas the 1 kV threshold, that's for your heavy-duty industrial stuff where you only care about a catastrophic event that could literally melt wires. It's all about matching the protection to the asset.
Moving on to integration. How does this data get back to that main system? I'm seeing UL-certified IEC 320 C14 inlets and the RS-485 protocol. That sounds a little like jargon.
Yeah, it does, but let's break it down. The C14 inlet is just that standard, tough, industrial-grade connector you see on most server equipment.
Okay, so it's familiar hardware.
Right. And RS-485 is just a communication protocol. It's used everywhere in industry because it's exceptionally reliable, especially over long distances or in electrically noisy places. And it all runs over standard CAT5 cable.
For up to 1,000 feet, I see. But what if that's not enough?
Well, that's where the flexibility comes in.
Right, it's compatible with a fiber extender. So you could put this sensor up to 1.2 miles away from the main unit. That's incredible.
It is. And that, plus the fact that it auto-configures as soon as you plug it in, makes deployment surprisingly easy.
And it's powered by the main system, too.
Yep, SIPs power, just 70 milliamps. It's really designed as a low-draw monitoring satellite. And with CE and RoHS approvals, it's ready for pretty much any market.
So to wrap this all up, what's the big takeaway for you listening right now?
I think the key thing is that this gives you high-precision, granular data on your power stability.
Right. It takes all that confusing electrical noise
Yeah.
and just transforms it into simple, actionable numbers. A count of swells, sags, and spikes.
And that's the intelligence that lets you prevent a system failure, not just clean up after one.
Which really leads to a bigger question, I think.
Go on.
If we can now proactively catch a destructive power spike that lasts for only a millisecond, how vulnerable are the rest of your environmental controls?
That's the thought to chew on. If your power is now monitored with this incredible degree of precision, what other unseen environmental factors are you missing?
Like what?
What about critical temperature gradients across a rack or subtle vibrations that build up over time? If you have a dual line power setup, what other factors might be just as essential to monitor in real time?